I'm Dr. Chris Creighton, and in this video we'll be learning about linear systems in 3 variables and how to solve them via elimination. Our objective here is being able to solve any system of equations via substitution or elimination, so we'll focus on elimination here for these 3x3 systems, and we're going to determine if these larger systems are unique, dependent, or inconsistent in that they have a unique solution, infinitely many solution, or no solution, and justify why. The system we're going to focus on in this video is x plus 2y plus z is 4, 2x plus y minus z is -1, x minus y minus z is -2. And we're going to solve this by elimination. So to keep track of everything, I'm going to label the 3 equations as R1 to be like a row, the first row equation, the second row equation for R2, and R3. So again, this is exactly like elimination, where instead of 2 variables, we have 3. And this scales up to more variables as well. So the basic premise here is that we want to start with one of our equations and use it to eliminate a variable from the other 2. I'm going to pick this x. So I'm going to use that x to eliminate the x in that equation and also the x in the third equation as well. If I use this x here to eliminate the 2x and the x in those other 2 equations, those other 2 equations get reduced down to just 2 equations in terms of y and z. So the first operation I'm going to do is I'm going to use the first row. So I'm going to use this one to eliminate the 2 and the 1 in terms of the x's in the other 2. So the first operation I'm going to do is R2 minus twice row 1. And so what I'm saying here is I'm going to take the second row, which is 2x plus y minus z is equal to -1, and then multiply the second or the first row here by a -2, so I get minus 2x minus 4y minus 2z is equal to -8. And then I add them, because like you can view this as like R2 plus -2 times R1. Honestly, that's how I think about it, in order to keep track of the negative signs. So when we add, the feature is we get a 0x there. We get a minus 3y there. We get a minus 3z is equal to -1 minus 8, which is -9. So now we've effectively eliminated that x there, so it has a 0 coefficient. So this new equation is minus 3y minus 3z is equal to -9. So effectively, I've replaced the second equation by this new equation without the 2x in front. And now we have it down to 2 variables. Likewise, we need a second equation in terms of 2 variables. So I am going to do row 3 minus row 1, which can be viewed as row 3 adding a -1 times the first row there. So again, I'm using the first row's x to get rid of the x in the third row. And you can either view this as subtraction or multiplying the first equation by -1 and then adding. It does not matter. It depends on your viewpoint. So row 3, we have x minus y minus z is equal to -2. And then minus the first row gives us a minus x, a minus 2y, minus z is equal to -4. So now we're going to add these two. So we get, again, that 0x, which is what we wanted, a minus 3y, which is great, a minus 2z, all right, is equal to a -6. So this eliminated the x from essentially the third row here, giving us the new equation of minus 3y minus 2z is equal to -6. Taking these 2 equations now, this gives us what I call a subsystem in 2 variables, so reducing it back to what we were doing in the previous sections. This is minus 3y minus 3z is equal to -9, minus 3y minus 2z is equal to -6. Now, focusing on solving the subsystem, we need to get y and z. There's a couple things to notice. First, this first row here everything is a multiple of 3. So if that's something you notice first, you can divide that first row by negative 3 and get y plus z is equal to 3. Or you can notice that we have a minus 3y in both equations. So that's what I'm going to do. If I notice that there's a minus 3y in both. If I subtract them, like this, we get a minus 3y minus 2z is equal to minus 6. So that's row 2. And we get a minus 3y minus 3z is equal to minus 9. And then we do subtraction. Or again, like I was doing in the first part, viewing this as multiplying by a negative, I get that negative y plus negative 2 subtracting negative 3 is negative 2 plus 3, so that gives us just a z there. And negative 6 minus negative 9 is negative 6 plus 9, which is equal to 3. So z is equal to 3. That gives us one part of our answer here. So now we need to go back and figure out, okay, what is now our x and y? Well, fortunately with these two equations here, we have some nice way of doing that. So now I'm going to use R1 in this equation here. So this one gives us minus 3y minus 3 times 3, which is our z here. And that's going to be equal to minus 9. So this is minus 3y minus 9 is equal to minus 9. Minus 3y is equal to 0, adding the 9 to both sides. So y is equal to 0. That is perfectly fine, and that can happen. Y can be 0, z can, they can be any numbers in actuality. So we have z is 3, and y is 0. Now, we need to figure out what x is. We know what y is 0. We know that z is 3, so now we need x. So I've moved our original system here. The original system gives us 3 equations in terms of x, y, and z. And you can use any of them to figure out what x has to be. I'm going to use row 3 of the original equation here. So that one will give us x minus, we know that y is 0, minus, we know that x is 3, and we know that this has to equal negative 2. So this simplifies down to x minus 3 is equal to negative 2. So x is equal to 1. This gives us our solution as 1, 0, and 3. And I just want to point out, to check it, check all equations in the original system. Being this one here. The point being is that if you check in any system after you've made modifications to the original, if you made a mistake, say going from row 2 minus row 1, for instance, if you made an algebraic mistake there and you check it after you made that mistake, your solution may work. But if you check it in the original system before you did anything to solve it, that will be a true indicator if the solution is correct or not. So again, take your solution and plug it back in. Just quickly stating here, if you can notice here that in the first equation we get 1 plus 0 plus 3 is equal to 4. That works. The second equation goes 2 plus 0 minus 3 is equal to negative 1. That's great. And then the third equation, 1 minus 0 minus 3 is negative 2, and that in fact works. So this solution works for each of those 3 equations.